Okay. Today, we're joined by Dr. Rachel St. Clair, co-founder and CEO of Simuli, a groundbreaking company at the forefront of AI and hyperdimensional computing. Rachel is a leading thinker on the intersection of computing, mathematics, and neuroscience with over 20 published papers and numerous citations. It's going to be a fun conversation. Welcome, Rachel.
Thank you. Thanks for having me.
Well, we are happy to have you here and happy to dive in because I have no clue what you really mean by hyperdimensional computing. So let's talk about it. Wait, actually, before then, Simuli, what is it? And then let's dive in.
Yeah, so I started Simuli because I really want to work towards this AGI technology future, right? This artificial general intelligence. And what I mean, my version of AGI, what I think of and what we're working towards at Simuli is something like data from Star Trek, The Next Generation, if you're
Mhm.
familiar. So something that is like us, that can help us and understand the world in similar ways that we do, but has a perspective that kind of breaks that human condition, right? Not constrained by the meat sack and the other things that we have as humans that keep us trapped in certain paradigms of thinking. So we're building a foundational model in AI towards that. It's a long-term project. And along the way, we'd like to help some of the issues in current AI space, such as scaling and how to handle data efficiently and properly. So those are the spaces that we're working on at Simuli, and like you said, it's all backed by the hyperdimensional computing that we work on. That's our tech stack. So.
Right. And the hyperdimensional computing, I mean, it's groundbreaking work because the way that you described it to me before we jumped on, it was like I've never heard of something like this before. So high level, what is it and why is it so different?
Okay, so it's actually a type of math. It's a new type of math. So you have your calculus, you have your algebra, you have, you can think of it this way, right? So if you've ever seen the show on TV on Apple Foundations, wonderful show, right? There's a part in that show where they talk about how our math that we use today is kind of like based on base 10, right? We count 1, 2, 3, 4, 5. But you can be on like base 3 or whatever, right? So you count in threes. So it's like 3, 6, 9, right? Hyperdimensional computing is kind of like switching to a different base, right? I'm just making an analogy here. It's not mathematically the same, but it's a different way of doing math. And that math is closer to something like quantum computing, where you have an abstract representation that represents something real and finite. So let's say you're representing data. The abstract representation that hyperdimensional computing provides is kind of mixed in, right? It's mixed in. It's not like what we have today where you have one number being represented by many bits. You have many numbers being represented by single bits. And that's how we get the abstraction. So obviously that has a bunch of fallouts for computing, like efficiency, like deeper thought analysis and symbolism in AI and stuff like that.
Right. So what does that actually mean in comparison to our current, quote unquote paradigm of computing, standard zeros and ones, bits? I mean, what does it actually mean in terms of performance, cost efficiency,
Okay.
data storage efficiency?
Yeah. Yeah. So what's cool about hyperdimensional computing, at least in the way that Simuli is attempting it, is that we do this thing that is basically data agnostic lossless compression as an encoding to represent the data. And I know that's a lot of nerd talk, right?
Yeah.
Basically, what that means here is that we represent our data in a way that is oftentimes compressed because you have many numbers being represented by single bits instead of the opposite, where you have one number represented by many bits, right? The data is represented often more efficiently, right? So you automatically are getting this processing done for a lot cheaper because anytime you process your bits, you have to process each bit. So if you're using fewer bits to represent the stuff, you have fewer operations. So just flat out, that's a savings right there. The other thing that you can think about that we're really interested in invested in here at Simuli is kind of the longer term play of hardware, where if you set this up properly, and many people have done, academic tape outs. We're the first company to really take this to industry, besides Jeff Hawkins at Numenta. Still quite academic. We're the first ones to kind of think about doing a volume as, large production run of hardware for this technology. And if you do that, you can really decrease the power usage. So when we think about AI, one of the biggest problems, if you've been following NVIDIA stock and that whole journey, is the power usage is insane,
It
right?
is.
And just throwing more chips at the problem of scaling AI. Oh, here we have more data, throw some more GPUs at it, right? But that's gotten us pretty far. But I think most people in the industry, OpenAI, everyone is starting to rethink whether or not that's a long-term strategy, right? And it can't possibly be a forever strategy. At some point, we're going to run out of power in the universe here. So, what we're trying to do is say, hey, you can use this technology of hyperdimensional computing to make you fewer operations. It's more efficient, right? You can use it in very strategic, creative solutions to reduce the overall power consumption. And so these things afford efficiency, but just on the computing side, there's also some cool information benefits, right? So you can do things like online learning. You can do things like this. The abstract representations are not quite the same as symbolic representations. So if you follow the AI space closely, you have your basic number predictors, right?
Mhm.
You're like,
Right.
what's the stock market going to be tomorrow, right? That's just normal stuff. You have your higher cognitive things, which, your graph networks and stuff like that, which are trying to say, like, which type of deodorant am I going to be recommended when I'm on Facebook scrolling or Meta or whatever, right? So those are trying to get into more symbolic representations of information. We're breaking that a step further and saying, hey, let's go into abstract space, abstract representations. So how creatively thinking can we get these AIs?
Got it. Okay, so it sounds like it's a better way of essentially storing and processing data to a certain extent. So the idea is that, well, you can't throw more chips at it. So instead, store it in a bit of a different way and process it in a bit of a different way. Because,
Uh-huh.
like you said earlier, you're not going bit by bit. You're going one bit, multiple different meanings. Next bit, multiple different meanings. I guess the question becomes: are we using the same type of hardware as we are today, like RAM, and are we still using CPUs? Are we using GPUs? Like, what? How different is it? Yeah, I sound so ignorant right now, but like, I'm just like curious.
Oh, so that's a really good question. So, what we're developing now, the products that we're launching this year, next year, all work on regular CPUs. Right.
Mhm.
They take your AI, it works on regular Intel chips, Mac chips, whatever. It's built like we're trying to solve this problem of AI scaling of where AI is at today
Right,
on the hardware it's running on today.
right,
So we do a lot of our engineers are very, very good. They do a lot of creative work to get this new technology to work on the old hardware, right? The old hardware is today's hardware. In the future, the paths that we're working down towards, the partnerships that we're starting today at Simuli, are gearing up for building new hardware eventually, right? It's a longer term pipeline because this is a very disruptive technology, right? This is very, very innovative, like you said. It's very different. It's out there. It's going to take a while to get to the hardware space. And we want to make sure that we have all the software that's going to run on the chips before we build the chips. It's just good business practice in our thinking. So,
exactly.
so yeah, the answer is both, just at different times.
Got it. So it'll make the overall industry much more efficient. So you have this goal of AGI or helping in pursuing AGI and making the overall process more scalable. And it seems like putting a nuclear reactor onto a data center just isn't the way. So what's like 2 to 5 year plan?
Yeah, actually, the nuclear reactor thing, not a terrible idea if they
It's
can
not
get the
terrible. Yeah.
technology miniaturized and safe. Yeah, not a bad idea, but I mean, we should be doing multiple approaches. This is a big, big problem, right? I mean, we're starting to build NVIDIA, other folks are starting to build data centers. They have plans now. They're looking for the space now where the abilities that the data center needs are basically going to consume all the energy of small countries. That's very scary. We
Yeah.
don't want entire countries and their populations being turned into GPU farms.
Right.
And that's not, I'm not pointing fingers at NVIDIA or anyone. This is everyone's problem. This is everyone's problem. The compute that we're going to need in the near future in this 2 to 5 year plan is going to be more than we really have the capacity for at this current moment. Right. So a lot of people are trying to find solutions. Nuclear reactors are one solution. Our solutions is to focus on the logic, to focus on how the actual data and model storage and processing happen and occur. So this year we're planning to work on some of the data technologies, or data agnostic lossless compression technologies. We're taking those to the cybersecurity space this year. Next year, we're focusing on getting what we call supernova. Supernova is our. I like to imagine the SpongeBob meme with
Yeah,
the
I
rainbow.
imagined it. Exactly.
We want Supernova. What Supernova does, that's our main current product we want to release in the next year, coming 2 years, right? It's very, very cutting edge. What we're doing is we're taking your AI, everyone's AI, of where it's already at. The model's already built, right? And what we're doing is we're running that through kind of an inference engine, a training and inference engine. So it will make training and inference cheaper because we're using the different math, right? So we're doing exactly what you're doing. We're just going to do it with different math. And that math is the HTC math, the hyperdimensional computing math, which is going to make it cheaper and more efficient. So that's our two-year plan, right? Yeah, 1, 2. And in the next 5 years, we're developing this foundational model, this AGI model. So this is based off principles in neuroscience of how you get higher cognition. And there's a theory by Andrew Coward from Australian National University. Brilliant, brilliant scientist. He worked at Nortel Networks, to offshoot of Bell Labs, which if you know anything about Bell Labs, is like that's where we got the transistor. That's where we got like radar, right? Sonar. We got all this cool technology from this World War II kind of government-backed monopoly that was working on these 30 years problems. So this scientist, Andrew Coward, has this theory called understanding cognition in terms of anatomy and physiology. So we borrow heavily for that in our new foundation model, which is basically the same principle of hyperdimensional computing, which is how many different Lego pieces can you combine to get more expression, to get better function, right? So we call this combinatorial expression, right? So HTC is the same way. That's the pseudo quantum nature. It's like, how many different things can I represent with one thing? That's the Lego piece question, right? I have this little yellow Lego. How many different things can I build with get like yellow Legos? What if I have yellow and red, right? So that's kind of our company's like outlook, is how to do more with less, right?
It sounds very, very high level, right? So the pilot that you guys are trying to run sometime soon to try to really hash things out, what's the end goal there? Are you trying to put together a technology that basically maybe it's just like a cloud type of integration, like a microservice that they just loop
Yeah.
into their overall workflow?
Yeah, so both, like we call it Nebuli. So Nebuli for security is what we're piloting this year. What it does is it takes all the data and it encodes it in a way that has this inherent security and immunity to it because of the HTC space, because it's abstract. Remember
Mhm.
that abstraction piece?
Yeah.
So now you have like this abstract piles of zeros and ones. So if someone comes to look at your data, good luck, right? They're looking at zeros and ones if they don't have your private key to look at it. Kind of like in crypto, we have private public keys, right? So if they don't have your private key, they really can't get back to your data. And we're setting this up. This, how do you handle data more efficiently? How do you represent it in this more abstract, secure way? That's a stepping stone on the way to this AI processing. Because anytime you're doing AI for any company, any application, you have two things you have to handle: your data and your model. So what are you going to be processing? Right? What is the stuff that you're trying to look at? And then your model is, how are you going to process it? How are you going to look at it? What are you trying to understand about it? Right? So we're focusing on the data piece right now. That's what we're rolling out this year, is how do we handle data? We're doing that separate away from AI and the cybersecurity place, just to really focus just on data. And then next year we're wrapping in the model space and saying, okay, how do I get the existing models to be computed more efficiently? Right? Because we want to use this new representation of data. How do I get the AI models to compute on this new representation, this abstract representation of data? So security, efficiency, and then higher order cognitive function. That's kind of what we're after.
I mean, it sounds like the right next step. It sounds like an actual pressing issue that people are dealing with right now, cybersecurity. I think if you were to actually sum the cost of cybersecurity overall, like breaches over the past year, it's like what, the fifth or sixth largest economy in the world. So it's a massive problem.
Yeah.
Now, quick question. I'm not trying to I'm just devil's advocate here. Quantum computing. People say that quantum computing, if it were to be applied to breaking through encryption, it would essentially breaks through almost anything except maybe quantum encryption. So I'm wondering, okay, so this form of cybersecurity, like, does that have it in mind? What happens when you throw a quantum computer at it?
Yeah. I mean, I can't tell you exactly what would happen if you threw a quantum computer at it, right?
Right.
But I have done some back of the envelope calculations, right? And these are back of the envelope calculations just means I literally was sitting there, had a thought, and was like, roughly, here's some numbers that might make sense, right? These aren't sound mathematical equations. But a couple things, right? Two thoughts come to mind. One, the encryption itself, the methods that we're using, right? They naturally fall out of how do you encode data? How do you use this data agnostic? It doesn't matter if you're using PDFs, Excel files, images, blah, 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 right? Does not matter. So any data we're looking at, how the process of encoding has this kind of natural encryption properties. And on top of that, we use a private seed. So the private seed kind of helps protect against the advanced quantum methods, no matter what, because it's very hard because you're not trying to guess the seed, right? You have to, the seed is kind of like a key, right? So the number of times that you'd have to guess what the seed could be has to be matched to the file that you actually have. So we could go into the nitty-gritty statistics. But the back of the envelope calculation here is that without, like, let's just say that you had this seed, right? And you're trying, or you don't have the seed, sorry, you don't have the seed, and you're trying to guess. Um, if you have a 640 by 480 image, right, not even 1080p, like, you have a low resolution image that you're trying to guess, right? And it's, let's just say that the back of the envelope calculation states that you need all of D wave's power to, like, untangle that,
Mhm.
to be able to get that without the seed. And if you're not familiar with I'm sure you're familiar with D wave, but D wave is a quantum computing company, right, that most of the US government employs, and I think Volkswagen employed for, like, they spent several $1,000,000 for 2 minutes of compute because that's how powerful quantum computing is, right? So, yeah, so it's gonna be pretty hard, even with quantum computing, as we think, but we're very soon we'll be releasing some formal testing on actual metrics of, how what we're gonna host at the hackathon and have,
That's cool.
people try to get at it because no one's done the formal test, right? This stuff hasn't hit industry yet. But yeah, and then the other thought that comes to mind on the quantum computing stuff is, why is there a need for a bridge, right? We're not replacing quantum. We're trying to bridge where we're at today with quantum computing of the future. We got about, I don't know, 9 to 7 years left. Another back of the envelope calculation. If you take the size of an atom and Moore's law, which says, we miniaturize every 2 years, we only got 9 years left to miniaturize. Then we'll be at the size of atoms, which means that we're already doing quantum computing once we reach that part, right? So we haven't got much time here, in order to get ready for quantum. So we're trying to help bridge that gap with something pseudo quantum.
Right. Pseudo quantum, the step before it, but to optimize for it. So how do you envision this, I guess, data storage method? I don't know how to properly categorize it. This
Yeah, 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 no.
paradigm that you're talking about,
Yeah,
working with quantum in the future.
yeah. So uh, how do we work with it? How does it work?
Yeah, how do you envision it actually working together with quantum?
Oh, yeah, no, it doesn't work with quantum, right? So that's what I'm saying. It's in preparation for quantum. It's to bridge this gap. It's to bridge this gap in the next decade until we actually get to quantum, right? We have good quantum computers. I mean, I think it's IBM's Qiskit package. Anyone can go for free right now and access quantum computers. It's fantastic. You don't get that many qubits, but if you're trying to learn, it's really cool, right? I mean,
Mhm.
they don't even pay me to say that. I've just used it and it's really cool and awesome. Google has a really souped up quantum machine, but until that's, like, running on my laptop, right? Until that's in every home, right? We have a long ways to go. Uh, and that's the same with, like, nuclear fusion. How do we miniaturize this stuff that's cost effective?
Right, exactly.
Is solving that problem. Someone else needs to figure that out. That's not what we're doing. But what we're doing is kind of giving them a little bit of runway and say,
Right,
here, well, we can implement these new compute methodologies till whoever's supposed to fix that figures it out, right?
right. So, interesting, interesting. I mean, Microsoft just recently made an announcement. I don't know if it's been tested by third parties yet, but they made an announcement that they Okay, maybe they made an announcement that they created a new form of matter, but I think the less casual one was, that they figured out how to put a quantum computer into, like, a smaller state, something that's actually, like, you can travel with it. I don't know, have you seen
Yeah.
those releases?
Yeah, no, they've been making a lot of advancements in that space. There's even a startup, I forget what their names is, but they claim to have gotten rid of because quantum compute typically needs very cold environments to run the machines. And there's some startup that's gotten rid of that, and they're just that team is like they're brilliant. But I think all the I mean, I'm not a quantum compute expert, right? You should have Scott Aronson or somebody, David Deutsch on this show to really talk about that stuff. I just think we can't go from the old von Neumann processing that we're doing today straight to quantum, right? I mean, we're running out of ways in which to make things more efficient, to make things smarter, and to make better use of the computation, right? Because like having more floating point operations. When you buy a new GPU, you say, how many teraflops, petaflops am I getting, right? We should really be basing that in how much energy expenditure it is. So petaflops per watt usage, right? And a lot of people don't think of the cost, right? They just like, the more flops, that's good. But it doesn't matter how many more flops you're getting if you're not actually getting more value out of the types of computing that you're doing, right? And so that's part of what we're thinking about too. It's great and all to reduce the energy expenditure. That's what we're focused on, right? We're estimating something like 3x power reduction, right? That's our target. That's our target for scaling AI. And that's great and all. But also, how do we also make the actual logic and types of software that we're running give more value? So we're not just trying to do more operations, we're trying to do better, smarter operations.
Right. And do you think that your approach is a step in that direction, that it does make that possible?
Yeah, we think so. We think so. And especially in our foundation model, that's what we're working towards, right? We're working towards, we use this combinatorial expression like the Lego thing I said to make it more efficient. But then from that, if you leverage what we've seen in human brains and animal brains and the like intelligence collectives of beehives, bee colonies, ant colonies, cities, right? Like collective intelligences. If you like learn from them on how they manage their resources, right? How they put together these little Lego pieces and what all they can build, you can learn some pretty cool protocols and examples for how you might get better types, smarter types of computation.
Right.
So that's what we're focused on long term.
It's fun. I didn't expect it to be almost like, I think the word is what, biomorphic?
Yeah. Yeah, it's neuromorphic. Neuromorphic is the slang the folks are using today. Yeah, no, but we took a lot of inspiration from biology because it's
Right.
a good example. It's just a good example, and it's not just we're not trying to recreate our brains in there. That doesn't help. I can make another baby. It's a lot cheaper than trying to rebuild a brain in a computer. And trust me, they're not cheap, right? So
Right.
if you have kids, they're not cheap. But it's still a lot cheaper than trying to recreate a new brain. So we're not trying to do that, right? We're just trying to borrow some principles and learn from good examples that we have.
Interesting. Okay, so, I mean, this idea of learning from nature, I've also heard of people experimenting with storing, what is it, information in DNA. Now, that sounds crazy, but the thing is, like, nature has already kind of figured out to a certain extent how to optimize for certain things. The amount of information in DNA is insane, the density of it. Right? Now, you guys seem to be doing something along that path. Not really, right? You're not storing things in DNA, but you guys are taking inspiration both from ant colonies, but also from the how the human brain works. And I'm wondering, can you expand a bit more on how you're doing that? How it's so different to the current neural approaches of conventional.
Yeah. Well, I mean, we're not the only ones. This has been like so. Hyperdimensional computing thought has been around since the 50s. If it was invented by Penny Nerva, right? So, I don't know if I said that already, but so it's been around and it's been coming up in academia quite a bit, right? We want to get with this technology so important and so needed that we're just trying to rush it into industry, right? And we're trying to do that in a responsible way, and do the testing and do the validation and put it into a vertical that really needs it, such as AI, right? So what we're doing is not so different than the DNA message that you're sending, right? The reason that DNA information has that expressive ability is because it's what we call in biology degenerate and ambiguous. So ambiguous means that from the same pieces, you like if you have the same things, you don't always get the same result, right? So when you're transcribing the DNA into proteins, sometimes you read this and you get that. Sometimes you read this and you get something else, right? It's ambiguous, right? It's not a one-to-one correlation. And degenerate means that sometimes I can make mistakes and it still turns out okay, right? So um, which is a very important principle for, how do you get things that aren't so brittle? How do you get software and computing paradigms that aren't brittle? To
Hmm.
where if you have a mistake, the whole thing doesn't blow up, right? You're no longer being like, why isn't it compiling? I have the wrong
Right.
letter in the wrong space, right?
Right.
Uh, so I think a lot of people are approaching this neuromorphic computing idea from like literally trying to figure out how does the neuron fire? How do we recreate that? And that's great work. A really good work has come from that. A lot of scientific insight that is trickled down into kind of bolstering the compute economy. A lot of that has been great. I think it's a really long pipeline. I think it's a very long task. It's a huge task to recreate a brain in a computer. It's a massive, massive task. And we just don't have the resolution to do it all. Can't see that far into the brain, right? Living ones, at least, right? We just really don't have the medical optical resolutions to really get the information we need to fully recreate. We're getting closer, and people are really trying, and I'm glad that they are. Our approach is to just take principles, to learn from a foundation first, right? This is kind of the mechanisms that happen in the brain, right? What's a good way of doing that mathematically in a computer? I mean, that's kind of our approach, right? It's like, hey, look, that thing happens over there. This is part of how they manage their resources in cities or in brains, right? And then we kind of got this protocol of like, this is what resource management looks like in intelligent design, system designs,
Hmm.
right? So we take a real systems engineering approach. We don't take a literal approach.
What sort of improvement would you say there is in taking this approach versus the current approach?
Yeah, well, I think it's where we can get there faster, right? Because it's not going to take us so long to figure out, quantumly how the brain is expressed if you're going down to that level, right? We basically already have the blueprints. We already have the system design specs. We already have that. Andrew Coward, neuroscientists, they've like we have a path. We have a path. We have a plan, right? What we need to figure out is exactly how to execute. Right, so that's why we've been working on this new type of math. And our engineers at Simuli, brilliant people, Victor Cavero, Peter Suter, the brilliant minds, right? And a lot of what they're doing is redefining a new framework for this math to live in, right? So we've basically come up with new equations, new mathematical equations. We said these equations can implement that plan, that protocol of resource management.
Interesting. Interesting. So you're basically finding like similar ways of doing the same thing except better. Simply put. So
Do it more efficiently, yeah.
yeah, interesting. So okay, we had a relatively I mean, I'm surprised by how deep we went before even hitting record, but we were talking about this holographic approach to bits. Maybe it'd be good to like dive into that real quick to understand and maybe share with everybody like what that actually means because holograms isn't the first thing that I personally think of when I start thinking storage or data expression.
So it's quite a technical concept to explain, and I can really go off on the deep end because I'm quite passionate about it. But we've been talking about how we like to have an abstract representation of data. And basically, what that means is we get more combinatorial expression. So we can build more with our little Lego pieces, our bits, right? Hyperdimensional computing, one of the principles it has is the principle of holography, right? It's holographic. And that comes literally from holography. So in the 1970s, we have laser holography. I'm not talking about the little stickers with that when you move them, you see two different pictures. I mean, that's kind of it, but we had way cooler stuff in the 70s of actual holograms. And basically, what happens is I don't know, there's a good video on this. I don't know if you wanna show
If I can share it while you keep
the
explaining.
video because, I can explain it if you put it on mute, but I recommend the audience looks at this video because it's really nerdy and it's really cool, and it's only, like, 13 minutes long. So, basically yeah, if you wanna start here. So, you shine 2 lasers of light, and we know that light is represented as particles and waves, right? So, let's think about light in terms of the waveform, right? So, you shine these 2 things of light at an object, and what's gonna happen is you're basically gonna have these 2 ripples, right? So imagine like in water, if you drop 2 rocks, it ripples out. And you see on the plate there how there's an interference where the ripples clash. That photolithographic plate, its job is to capture this interference where the waves crash. You can pause it. So when you shine the light back through that photolithographic plate that is captured, the stuff, what's going to happen is it's going to recreate the original ripples,
Mm.
right? So you're going to get the actual image that's created from that interference of the 2 waves together. And that interference capturing is exactly what we're doing with HDC. Not, so we're using this principle of holography which is natural to hyperdimensional computing, right? In order to say, hey, all we need is the interference pattern. We don't need the original ripples. So think about that in terms of data. I don't need the original data. I only need the interference pattern of the data. And from that, I can reconstruct the whole data. Just from a part, I can reconstruct the whole data. Right. And so that is the power of how we get efficiency out of this HDC stuff. That's kind of a deeper tech explanation. Does
Yeah,
that
and
make
that
sense?
I have to say that matched the video really well. Round of applause, I have to say. Very
Thanks.
well done.
I've watched that video like 500 times. It's great.
Well, I mean, they were doing really cool things in the 70s, I have to say, 60s and 70s. Things that I didn't think that were possible.
We actually had this is a fun fact, right? We actually had like Apple FaceTime way back in Bell Labs. They did Apple FaceTime, and what they found was people just turned off their video because they didn't want to see themselves. So it didn't stick in the market. They tried to take FaceTime to market like way back before Apple was even around, right? Before Apple was even a company, and people are like,
That's
nah,
insane.
I don't want to do
Cannot
that.
believe that. Oh my.
Yeah,
It's just it has to match when people are ready for it. And
yeah,
that's half the problem.
yeah.
But in the end, I mean, it sounds like you're really up to a lot of really interesting things, cutting edge, the type of stuff that I like love, right? I have to say.
Thank you.
Now that said, I have to say you're also the CEO of the company, so I can imagine that having the type of conversations where you're talking about deep tech with investors, the investors have to understand, but it's like a different beast than just being a regular founder for a business. So, what's it like leading something like this?
It's wonderful. It's wonderful because the people that get it and the engineers, the teams that we're building, the people that we want to partner with, the people who are attracted to what we're doing, they're really into this disruptive technology space. They're really thinking about 30 years from now, what's the world going to look like, right? They're on the edge. We're on the edge, right? We're excited to be here. We're excited for the people that get it, and bringing the people up to speed can also be challenging, right? People that, I don't want to talk about the tech. I want to talk about the ROI, right? And so for them, what we've seen is this stuff is a bit magical. Sounds like magic wand, right? Because it
A
is
bit,
magic. It's highly disruptive. It's really cool, and it
right?
does work, right? And we need to show them that it works.
Mm.
And so that's what we do for the folks that are like, hey, don't talk tech, show me what you got. We show them that look, this is it. This is our data agnostic lossless, encoder. This is how it's running. Like, come look at it, right? And then we're running pilots with other large clients in the industry to say, hey, look who's using it. Look how much they're saving, right? It's a show and tell as well as like storytelling. Show and tell and storytelling is really where it comes from. But it's really exciting because I get to talk to people like you. I get to talk to people who are excited about what the future could be. And that's I had really great advisors and mentors who were like, it's great to work on long-term problems.
It
We
is.
don't need to work on, I'm not interested in the LLMs and the cheap apps and stuff. I use that stuff every day, great technologies, right? But my focus is, and someone has to do the job, everyone has to take different parts of what we're going to build in the future. I'm thinking 10, 20 years out, right? And we're doing stuff along the way to get there. There's stepping stones, right? But this is a long term company and it's exciting, to kind of be paving the way and carrying the vision.
Yeah, I can imagine. I guess it comes with the territory to a certain extent when you're as smart as you are, right? To get to work on these type of things, right?
Yeah.
Um, and I mean, it really is like insane stuff.
I've been really let me just say, I've been really fortunate to have a lot of really good business people, like our COO, Benoit Sayed, other people that we work with, right? That to kind of help guide the company, right? So I really take a lot of parts in the technology aspects and the vision and what we're really trying to do and day-to-day operations, things like that, regular CEO stuff. But I do have a lot of support from people who have been in much larger companies who are backing kind of the business exploration. So I'm just thankful for the support of those people, right?
Right, right. I mean, it takes a team to get something like this off the ground, but it seems like if you guys get things to where you guys already envisioned, then it's gonna really change the way that the world functions. But ultimately, it seems to me like uh, you do need like the team to get to the place where you're going to be, and you are going to save some small nation worth of energy and some small nations generally from becoming CPU farms, which is always a great thing to do, right? All in a day's work. So it seems like Rachel, like you guys are basically putting together a team that has is positioned to really change the world, and I'm really excited about it. I'm wondering, so for this pilot act, who would be the perfect people to work with in that?
Right. So essentially what this technology does is it offers a layer of encryption. If people that are trying to send sensitive data, right? So think about people who might be using on-prem storage, like your financial institutes, your pharmaceutical companies, people that have very sensitive data, even people like musicians, CAD designs, right? Things that you don't want to be treated as regular things. You want it to be treated as, trademark secrets or intellectual property, right? I mean, this technology is going to be kind of very essential for just day-to-day ops of sending those files, keeping those files, right? So one of our biggest target clients is kind of the larger cloud providers, right? That's kind of our end goal, is just get this stuff running on all the infrastructure. We're really focused on infrastructure level solutions because we don't want to leave it up to the users. I don't want to be having to use these technologies and navigate all this stuff. I want it to just be built into the stuff I'm using. But I don't want to have to go click the buttons to make sure my stuff's secure. I want the computer people who are running the computers and the internet and that stuff. I want them to handle this. So that's why we're targeting those infrastructure level clients. Yeah.
So we're running up on time at this point, and I want to be really respectful of your time. So thank you for taking this long, this much
Thank
out
you
of your
so
day.
much. Can
So
I ask a question back before we
yeah,
go?
yeah, for
I
sure.
mean, what do you think of all this, right? I mean, how would you use some of the stuff we've talked about in what you do in your daily operations, right? I mean, I like feedback. Make this two ways.
You know, based off the conversation that I've had, I've been talking to AI engineers as
Mm.
well as AI cybersecurity specialists, and I think one of the main angles is this idea of protecting against a potential threat in quantum, the current threat in AI, current new threat in AI, and handling an existing threat, which is cybersecurity generally. Um, that angle would work, I believe.
Yeah. Yeah, I think so. It's interesting. You must have a lot of experience to be able to pick that up because I know what we talk about is quite dense at Simuli, right? So I'm glad that that's hitting home, right?
That initial part, but honestly, to me, it seems like I've multiple times throughout this conversation, I've just kind of been wishing to myself that I could like watch a lecture real quick, even if it's like
Yeah.
2, 3 hours, to really understand the like the details of it. Because
Mhm.
if applying it is where there's a gap right now in my mind.
Right.
The video that we saw, it looked like it was okay. Is there glass involved? Is it really just software? It just you know?
But yeah, we have a ton of lectures, I have a ton of lectures and talks out there. Our top engineer, Peter Suter, he has a ton of lectures out there. You can look this stuff up. You can see what we're doing at more technical involved levels for sure.
Sweet.
But yeah, it's been really wonderful getting to discuss with you what we're doing at Simuli on here. So I really appreciate the
Yeah.
opportunity.
Yeah, and listen, I'm thrilled by the opportunity to be able to do this. By the way, where do you lecture? Where do you all lecture? Is it like
Well, we get asked to speak at a lot of different places. Oh gosh. So I mean a lot of our stuff is on YouTube. I mean that's where I like to pull a lot of my information, right? I mean besides academic papers and textbooks, blah blah blah, right? But
Right.
YouTube is where it's at. That's where you can find us. That's where you can find a lot of our stuff. If you go to our website, simuli.ai, we have a blog section.
Mhm.
Blog section includes YouTube's papers. We try to update that, but honestly, we've been really heads down focused on product building
Right.
and product delivery to clients. More to come very soon. Hopefully, you'll just see our technology out in the world. Maybe you'll be using it and you won't even know. So,
That's the hope. Honestly, that's the hope. Well, Rachel, I really appreciate your time. Hopefully this is the first of many.
yes, thank you so much. Take care.